The first derivation from this chapter is electric potential due to point charge. Now we have a charge q which is at point O. There is another charge q naught which is lying at infinity, right? And the distance between OP is r, and the distance between O and n, let's say it is x. Okay. Now first we have to bring this q naught charge from infinity to particular point n, and the small displacement in this bringing this charge from q naught to n is dx, and the distance between O and n is x. Okay. Now what will happen when it will move here to here and the small displacement, then the amount of work done, small amount of work done in bringing a charge q naught from infinity to n, dw can be written as force dot displacement is dx, right? Now what is the force? The electrostatic force when the particle is present at n due to this charge q can be written as k q naught, and this distance between O and n is x square dot dx, right? Now when we remove this dx, we will get k q naught upon x square dx cos theta, right? Now the value of cos theta, the force due to this plus charge, this is also plus charge, this is also plus charge, the force due to this charge will be in this direction, I can say in this direction, and the displacement of a charge particle is in this direction. So displacement is in this direction, so we can say the angle is here 180 degree. So cos 180 degree will be equal to minus of 1. So this work done will become minus k q naught upon x square dx is equal to dw. Now to find total work done, total work done in bringing a charge of 1 coulomb, let's say 1 coulomb. So q naught is equal to 1 from infinity to r. So we'll integrate both sides, dw here minus k q naught, here we have 1 upon x square dx, and the limits are infinity to r, right? Now here minus sign is common, k is common, q naught, 1 upon x square integration can be written as, here power is positive, it will go in the numerator and power becomes negative, so this will become minus 2, we'll add 1 in the power and add 1 in the denominator, and limits are minus infinity to r. So plus minus minus, so x minus 1, here we will have minus 1, the limits are infinity and r, and we have minus k q 1, the value of q naught is 1 here, so we will write 1. So we will get expression from here is k q, the power is negative, so it will come in the denominator, 1 upon x, this negative sign and this negative sign combine and becomes positive. Here we have infinity and r, we will put upper limit here 1 upon r, and then we will put the lower limit 1 upon infinity is 0. So we left with the answer k q upon r. This is electric potential due to point charge. Okay. Another most important derivation from this chapter, electric potential due to an electric dipole at any point, right? In our previous chapter we had discussed electric due to dipole in axial line as well as in equatorial line, and this is the electric potential at any point. So after knowing this point, we can find the electric potential at axial line as well as in equatorial line. So let us start with the derivation. First of all, we have electric dipole, that is A and B, minus charge is at A and plus Q charge is at B, and the distance between A and B we know that this is 2A. O is a midpoint, so we can write that AO is equal to A and OB is also equal to A. Okay. Now the distance between Q2 plus Q2P is R1. P is a point where we have to determine the electric potential, and the distance between A and P is R2, and the distance of O and P is R. Okay. Now we know that the electric potential due to charge at A is equal to, can be written as V1, and V1 is equal to Q upon 4 pi epsilon naught. V1 is equal to Q upon 4 pi epsilon naught R1. Similarly, if I have to find the electric field due to charge plus Q, that will be equal to V, this is my V1, this is my V2, this is equal to Q upon 4 pi epsilon naught R2. Okay. Now we have to find the value of R1 and R2 in terms of R and A. And how we are going to do that thing is, we'll draw a perpendicular from B to OP, that is a M, and we are going to draw perpendicular from A to OP. We'll extend this OP up to N and we'll draw perpendicular here. Angle is 90 degree and this angle is theta. This angle theta, this is also angle theta because they both are vertically opposite angle. Now this is the A. Using Pythagoras theorem, we can find the value of OM. How we can find this? This is angle theta and this is 90 degree. This is A and I have to find this thing, right? So I know that cos theta, I have to find this OM, and the cos theta is equal to base upon hypotenuse, right? So base is OM, I have to find, and hypotenuse is A. I'll multiply it, I will get A cos theta. So my OM will be equal to A cos theta. So the value of R1, this R1 can be written as R minus A cos theta, because if we draw perpendicular, the lines become equal. Always remember, if I am drawing the perpendicular line to a particular line, the length of both line becomes equal. Now this my OM, this my PM. PM will be equal to PB. Always remember, when we draw a perpendicular line, the length of lines become equal. Okay, so PM can be written as R minus A cos theta. So my R1 becomes R minus A cos theta. Similarly, this is my A and this will become A cos theta. So I can write R2 is equal to OP plus ON. So R2 is equal to R plus A cos theta, right? So I'll substitute the value of R1 and R2 here. I will get Q upon 4 pi epsilon naught R minus A cos theta, right? And here I will write V2 is equal to Q upon 4 pi epsilon naught R plus A cos theta. As we know, the denominator of V2 is greater than denominator of V1. We have more denominator, the value will be lesser. So we can say that V2 is lesser than V1. So to find the net potential, we will subtract them. So we will get V1 minus V2. So I'll put the value of V1 and V2 here. Q upon 4 pi epsilon naught is common in V1 as well as in V2. So I'll take it common, Q upon 4 pi epsilon naught. I will left with the 1 upon R minus A cos theta and R 1 upon R plus A cos theta. Now I'll take the LCM. A minus B, A plus B. We know the formula, A minus B, A plus B, that will be equal to A square minus B square, right? So this is my A, this is my B. I can write A square, it means R square, and B square means A square minus cos theta. This will go here. So I'll get R plus A cos theta and this will get R minus A cos theta. Okay, A cos theta, R is cancel out with the R. Sorry, here we have subtraction sign. So let me solve it for you. What I will get, Q upon 4 pi epsilon naught. This is R square minus A square cos theta. I'll cross multiply, here becomes A R plus A cos theta. And here I have minus R plus A cos theta. R is cancelled out with R. I am left with a 2A cos theta. So my answer becomes Q upon 4 pi epsilon naught 2A cos theta upon R square minus A square. Right. Now this Q and 2A, I know that this is equal to P. So I can write P cos theta upon 4 pi epsilon naught R square minus cos square theta. If cos theta is very less, I can neglect A square. If A square cos theta is very less than R square, so I will neglect this expression. So I am left with a P cos theta upon 4 pi epsilon naught R square. Also in terms of a unit vector, I can write P vector dot R cap upon R square. Special cases, for equatorial plane, we know that equatorial plane is always perpendicular plane, and for that theta is equal to 90 degree. If theta is 90 degree, cos 90 is equal to 0. So electric potential becomes 0. For axial line, we know that theta is equal to 0 and cos 0 is 1. Cos 0 is 1. So this becomes 1. We are left with a P upon 4 pi epsilon naught R square. For a point charge, always remember V is proportional to 1 by R, and for a dipole, V is proportional to 1 by R square. Okay, next we have important topic, that is equipotential surface. Now as the name suggests, equipotential, it means the potential at every point of the surface will always remain same. If potential is same, then we can say the potential difference is 0, right? If potential is same, if something is same, then change in that thing will be 0. I can say potential difference is 0. If potential difference is 0, so I know that potential difference is equal to work done upon charge. If potential difference is 0, then work done will be also 0. So we can define the equipotential surface is that surface at every point of which potential remains same, or the potential difference is 0, or work done in moving a charge from one point to particular point, is always 0. This is the definition of equipotential surface. So let us read. An equipotential surface is a surface where the electric potential is same at every point, meaning no work is required to move a charge along the surface. As I already told you, an equipotential surface is a surface where the electric potential is constant at all the points. Moving a charge along the equipotential surface requires no work done. There is no potential difference between the 2 points. Electric field is always perpendicular to the surface. Sometimes there is MCQ questions comes in exam. So we should know the properties of equipotential surface. The first property, work done 0. The first property is potential difference is 0. Work done is 0, and electric field is always perpendicular to the surface. Now why electric field is always perpendicular to the surface? Because we know that there is a angle of cos theta between the force and the displacement, right? And if the theta is equal to 90 degree, this is the only case when the work done will be equal to 0. Theta equal to 90 degree means the electric field, that is electric force, is always perpendicular to the surface, right? Electric force is perpendicular to the surface. So we can say that electric field is always perpendicular to the surface. The electric field lines are always perpendicular to the equipotential surface at every point. Conductors, the surface of conductors in electrostatic equilibrium is an equipotential surface. So surface of a conductors always act like a equipotential surface because the charge inside is always 0. So there are problems that come in an exam, that we have to draw equipotential surface for a point charge, for plus charge, for minus charge, and for a plane. For a plus charge, electric field line always act outwards, and equipotential surface is always spherical in shape. Similarly, if I am having a same charge, this is positive charge, this is negative charge, or it will be negative charge and negative charge. The equipotential surface is spherical here, and it will weigh and repel each other if two charges are placed near to each other. If I am having a same kind of charge, then the equipotential surface will be like this. For a plane, it is always perpendicular to the plane. If my plane lies in xy direction, then the equipotential surface is always in z direction. Always remember, the equipotential surface is always perpendicular to the plane. Now there is another problem come which is related to relation between the electric field and the potential. Now we know that work done is equal to change in potential. Work done is equal to change in potential. We already know this. So work done can be written as Q VB minus VA. VB, this is a B surface and this is a A surface. We have to move a charge from A to B. So A to B, B is the final position and A is the initial position. So work done is equal to VB minus VA. So I can write work done is equal to Q naught VB minus VA. I will divide Q naught here. So dW upon Q naught will be equal to VB minus VA. Now this VB, the potential at B is equal to V plus dV, because V is the potential of A. V is the potential of A, and this small displacement is equal to dV. So I can write the potential at B. VB is equal to V plus dV. I will put my value V plus dV here, and the potential at A is V. V is cancelled out with the V. I left with the dV. So dW upon Q is equal to dV, right? So I can also write dW is equal to this Q naught will go here, Q naught dV. Now work done, I know that work done due to electrostatic force is equal to minus F dr, right? So for electrostatic force, we know that this is equal to Q into E. I'll put the value of F, this is QE dr. Equation 1, equation 2, I'll equate them. Minus QE is equal to Q dV. Q is cancelled out with Q. We'll get E here and we'll divide dr. So we'll get E is equal to minus dV by dr. This is a very important expression, that electric field is equal to V upon L, or we can say that electric field is a gradient of potential difference, is gradient of potential difference. Gradient means if something is changing with the distance, like rate means if something is changing with the time, and if the quantity is changing with the distance, that is known as gradient. So we can say that electric field changes with the change in the potential. If potential is changing with the length, we can say electric field also changes. Okay, important notes: potential energy of a system of charges. If you have to find the potential energy, then what we'll do, it is equal to work done, and work done is equal to q1 q2 upon r. Okay, so this is equal to u is equal to 1 upon 4 pi epsilon naught q1 q2 upon r. If I have to find the potential energy due to multiple charge, then potential energy due to 1 2, if there is a triangular surface, and I have to find the electric field due to 3 charges. I said this is 1, this is 2, this is 3. So first of all I will find the electric potential energy between 1 and 2, then 2 and 3, and then 3 and 1. This will equal to q1 q2 upon 4 pi epsilon naught r1 2 r2 3 r1 3, and charges are q2 q3 q3 q1. Important result, and important result, last important result is potential energy of a system of 2 charges in an external field. If there is another field which is present in the system, then we can written as q1 v1 q2 v2 plus 1 by 4 pi epsilon naught q1 q2. The electrostatic potential energy due to these two charges due to q1 and q2. Okay. Next important derivation is potential energy in an external field. So whenever dipole is placed in a electric field, it will experience a torque, and we know that that torque is equal to Pe sin theta, right? This torque aligns the dipole in along the direction of parallel to the field. Now the amount of work done in rotating the dipole, if dipole is rotating, then it will done a work, and that work done is equal to Pe sin theta dot d theta. We have to find the total work done in rotating this dipole from theta 1 to theta 2. So we will integrate theta 1 to theta 2 Pe sin theta d theta. Pe is common, we will take it outside, the integration of Pe. So different integration of sin theta is equal to minus of cos theta. So this becomes minus cos theta, we will take minus sign outside. We have to integrate from theta 1 to theta 2. We will put the value upper limit cos theta, and then we will subtract with the minus cos theta. This work done is stored as a potential energy, and potential energy due to dipole is equal to minus P dot E or Pe cos theta. This is important result we have to learn. Next is dielectric and polarization. Now what are the dielectric? As I already told you in my previous video, dielectric are the material which get polarized when they are placed in electric field, and they create a pole, that is positive and negative poles. Those molecules which create a pole, they are called polar molecules, and which molecules whose positive and negative charge coincide, they are known as a non-polar molecules. Now polarization is the same phenomena. Whenever we are, for example here we are having a dielectric slab, we will place it in electric field, and the direction of electric field from positive to negative. Okay, now here we have positive charge, so negative charge will develop from here, and this is called polarization, that there is a development of a polarity or a pole molecule get polarized, that is separation of positive and negative charge take place whenever a dielectric material is placed in the electric field. And the net electric field appear inside this dielectric. This is direction of this is from positive to negative. So E will be net, E will be equal to E naught. This is E naught applied electric field minus EP electric field due to polarization, which is opposite in direction. So net E is equal to E naught minus EP. The value of E naught upon E. Dielectric constant K can be written as E naught upon E, where E is equal to E naught minus EP. We know that the electric field, net electric field after the polarization is always less than the applied electric field. So we can say that K is always greater than 1. Dielectric constant is always be greater than 1. Next important term is polarization vector. P vector can be written as dipole moment upon volume, and we know that dipole moment is equal to Q into 2A upon V. This is not a cross product, this is simple multiplication. Polarizability, the tendency of a substance to polarize, is called polarizability, and it is equal to alpha into E is the applied electric field. So we can say that polarizability depends upon the applied electric field. That polarizability is also proportional to the surface charge density. More will be the charge on the surface, more will be the polarization. Electrical susceptibility means how much material can be polarized when they are placed in electric field, that is a susceptibility. The polarizability is proportional to E epsilon naught. Epsilon naught is permittivity here. When we remove the sign of proportionality, we get a constant which is susceptibility. So we can say chi is a susceptibility which will define that material is going to be polarized easily or it will be difficult to polarize the material. Susceptibility depends upon the nature of dielectric material. It depends upon the nature of material, right? So we have to learn this expression that polarizability P is equal to psi E and E. E is a electric field that is developed. So we have to find the relation between the susceptibility and the permittivity. We know that electric field, net electric field after the polarization will be equal to applied electric field minus electric field due to polarization. This is the electric field due to polarization, right? So we know that the electric field due to polarization is proportional to polarizability. More will be the polarizability, more material can polarize, and more will be the electric field. So electric polarization is proportional to polarizability. So E can be, I know that E can be written as E naught minus P upon epsilon naught. This EP is equal to P upon epsilon naught when I remove the sign of proportionality. So I'll put the value EP P upon epsilon naught, and the value of P I know from here. I'll put it psi epsilon naught E. Epsilon naught cancel out with the epsilon naught. I'll left with the E only. This E, this psi E will go this side and becomes positive. I'll take E and E common. I'll left with the 1 plus psi, and here we have E naught. I'll divide E naught by E. So 1 E naught by E, I know that this is equal to dielectric constant K. So 1 plus psi is equal to dielectric constant. This is an important result. Next is what is a capacitor and what is a capacitance. So capacitor is a material, is a conductor carrying a charge plus Q and minus Q, and they are kept a distance D apart, is called capacitor. If I am having two parallel wires, conductors, okay, and they are used for store the charge. The plus Q charge is placed at this plate and minus Q charge is placed at this plate. Okay, this kind of conductor is called capacitor, and the charge is proportional to the potential difference. More will be the charges, more will be the potential difference. When I remove the sign of proportionality, I get a constant C, which is called capacitance of a capacitor. So I can say that that capacitance is directly proportional to charge and inversely proportional to potential. If I draw the graph between the Q and V, this slope will give the value of capacitance. Okay, the SI unit of capacitance is farad or microfarad. Now next important derivation is capacitance due to parallel plate. I have two parallel plate. Surface charge density of this plate is plus sigma and this plate is minus sigma, and I have grounded this plate through earthing. Consider two parallel plates and the distance between the plate is D. I know that from the application of Gauss law, the electric field due to this one plate is equal to sigma upon 2 epsilon naught. Electric field due to other plate is sigma upon 2 epsilon naught. The net electric field will be equal to, I'll sum up them. I'll get 2 sigma upon 2 epsilon naught. 2 is cancelled out with the 2, so I'll get sigma upon epsilon naught. So E will be equal to sigma upon epsilon naught. I know that sigma is surface charge density here, and sigma will be equal to Q upon A, that is charge upon area. I'll put Q upon A epsilon naught. Now the capacitance, we know that this is Q upon V from the definition of capacitance. Q will put here, and we know that V is equal to E D, because potential is gradient of, electric field is a gradient of potential. Electric field is a gradient of potential, right? So I'll put E into D. The value of E, I'll put it from here, Q upon A epsilon naught. Q is cancelled out with the Q. I'll left with the A epsilon naught upon D. This is a result due to parallel plate capacitor. This is capacitance due to parallel plate capacitor. The next most important derivation, capacitance of a capacitor when the dielectric slab is placed between the capacitor. Now this is a dielectric slab, and we know that whenever this dielectric slab is placed in the electric field, they get polarized, and the electric field due to polarization is in this direction opposite to the applied electric field. This is the applied electric field E naught, and this is a electric field that is developed within the thickness T. T is the thickness of dielectric slab, and D is the distance between the dielectric slab, between the parallel plates, and T is the thickness of slab. T, thickness of slab. D is a separation between the plates. Separation between the plates. Okay, now we know that electric potential between the plates, V will be equal to, now there are two electric field, this E naught electric field act in the thickness D and this EP act in the thickness D minus T, right? Sorry. This EP will develop in the thickness T and E naught will be acting in direction D minus T. In D minus T, this is complete D, this is T, so D minus T in this area the electric field E naught will act, right? Now we know that K is equal to E naught upon E, so we can find the value of EP, which is E naught upon K. I'll put it here, E naught upon K T plus E naught D minus T. Change my pen. D minus T, I can take E naught common from here, I am left with a T upon K plus D minus T, right? This is my potential. Now I know that from definition of capacitance, C is equal to Q upon V. Q is equal to, we know that in terms of surface, and we know that electric field due to plate is equal to sigma upon epsilon naught, and sigma is equal to Q upon A epsilon naught. Sigma is a surface charge density which is written as Q upon A, right? So what I will do, I'll add Q here, and we know that potential V is, I can write E naught T upon K plus D minus T. The value of E naught, I'll put it from here, so I'll left with a Q upon Q, A upon epsilon naught will go in the numerator, T upon K plus D minus T. Q is cancelled out with the Q, so I left with the expression A epsilon naught upon T upon K plus D minus T. This is an important result due to electric capacitor, due to when dielectric slab is placed inside the capacitor. Now if we have to find for a metal conductor, what will happen if instead of dielectric slab we place conducting metal? Okay, we know that for conducting metal K is equal to infinity from electrostatic shielding. So K is equal to infinity, so T upon K will be equal to 0. So our result becomes A upon epsilon naught D minus T. So I can say that capacitance due to dielectric slab is greater than capacitance due to this metal slab. Okay, these are the important results, important derivation from this chapter. Apart from that, we left with the two derivation. Number 1, when capacitor is arranged in a series, capacitor arranged in series, capacitors in parallel, capacitor in parallel, right? So when capacitor are arranged in a series like this, and capacitor when arranged in a parallel like this, so we know that in series what remains same? This is a battery. This is my C1, this is my C2, this is C3, this is a C1, this is C2, this is C3. Now in series Q remains same, Q remains same. In parallel we already know from the resistance in our 10th class, V remains same. So if I write C1, I'll write C1 Q1 upon V1, I'll write C2 that is Q2 upon V2, I'll write C3 that is Q3 upon V3, right? But in case of series we know that charge remains. So I can write V1 is equal to Q upon C1, V2 is equal to Q upon C2, V3 is equal to Q upon C3. So my net potential will be equal to V1 plus V2 plus V3. I'll substitute the value of V1 that is Q upon C1, Q upon C2, Q upon C3. This is V. Take Q common and divide V upon Q is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. This V upon Q equal to 1 upon Cs. So I can write, in case of series, they will reverse and add. Capacitance will reverse and add itself, right? While in case of parallel, V is same, so I can write C1 is equal to same. V1 is same, so C1 will be equal to Q1 upon V. I can find the value of V. V is equal to, sorry, I can find the value of Q1 from here, that is C1V. Similarly, Q2 will be equal to C2V and Q3 will be equal to C3V. So net charge Q will be equal to Q1 plus Q2 plus Q3. I will put the value of Q1, that is C1V, C2V and C3V. This is Q. I will take V common, I will divide. Q upon V equal to C1 plus C2 plus C3, right. So this Q upon V is Cp, capacitance in parallel, which is equal to C1 plus C2 plus C3. So in case of parallel, capacitance add directly, and in case of series, they will reverse and then add. After that, we have common potential. If we are having two potentials and we have to find the common potential of this capacitor, then this is equal to C1 V1 plus C2 V2 upon C1 plus C2. This is an important formula for the common potential if two capacitors C1 and C2 are joined and they are having common potential V. So these are the important derivations and concept from the chapter electric potential and capacitance. Okay. So by doing this derivation, we have done all the chapter questions or the derivation of unit 1 electrostatics. After that, we are left with only numerical, which I will be discussing in my next video.